Right, topic 12, acid-base equilibria. Now, we're just going to do some basics today, basic definitions and ideas about this Bronsted-Lowry theory. So let's have a look at the following reaction. We know that when a weak acid, in this case ethanoic acid, dissolves in water, then it only partially dissociates. So only some of these molecules react with water molecules to produce this ion, the H3O plus, and ethanoate ions. Now remember that H3O plus ion had a special name. It was called the oxonium ion. Sometimes you will see in text that it used to be called the hydroxonium ion, or sometimes the hydronium ion. So it goes by lots of aliases, but we're going to call it the oxonium ion. Okay? Now this is the ion that is responsible for acidity. We've always said that it's H plus aqueous, but essentially H plus aqueous is this, because a H plus is just a proton, and a proton can't exist on its own. It's far too reactive. Okay, so H3O plus is the oxonium ion. This equilibrium lies heavily to the left. So the majority of molecules are on this side, and there are very, very few of these. Okay, to get a picture. The one in every, let's say, 10,000 molecules, one in every 20,000 molecules might react with a water molecule to form these two species. Okay, so it's not very much. Now we have to start with definitions, like I said. So what we say is, on the left-hand side, the ethanoic acid is behaving as an acid. We'll talk about that in a second. So we call that acid 1. Now that's linked with the ethanoate ion. The relationship is a proton, H+. So we call the ethanoate ion base 1. On the right-hand side, the species that now has the proton that can be given to other species is the H3O+. So we call this the acid 2, and that's related to the H2O, and the H2O is base 2. Okay? They're called conjugate acid-base pairs, but we'll talk about that a bit more in a second. Now this is Bronsted-Lowry theory, and in this theory we say that an acid is a proton donor. This is very IGCSE, isn't it? And a Bronsted base is a proton acceptor. Okay, so the relationship between an acid and a base is mediated with a proton. If it loses that proton, it's becoming a proton donor, it's an acid. And if it gains a proton, it's a base. So the ethanoate ion is called the conjugate base of ethanoic acid. This ion, base 1, is the conjugate base of ethanoic acid. And here, the H3O plus ion is called the conjugate acid of H2O. It's all definitions. Just let them sink in. It's a bit new at the moment. Okay, we also say that the ethanoate ion and the ethanoic acid are conjugate pairs, and the H2O and H3O plus are conjugate pairs. We could split the equation up into two kind of half equations, couldn't we? So again, it's the proton that determines this relationship, doesn't it? So the ethanoic acid, acid 1, loses that proton to form base 1. There's the proton. And then that proton is accepted by base 2 to form acid 2. So let's consider this reaction. Now we know that ammonia is our weak base. So when we dissolve ammonia, it's very soluble because it hydrogen bonds with water molecules, doesn't it? So it's very, very soluble. I don't know if you've seen the fountain experiment. You might want to Google it. We did this in class, so we did the fountain experiment where ammonia dissolves so fast that it causes pressure to decrease in a flask and a fountain to appear. So it's extremely soluble. But when you dissolve it in water, only some of the molecules, the ammonia molecules, undergo this reaction. They react with water molecules to produce ammonium ions and OH minus. And we know that OH minus is responsible for alkalinity, isn't it? For alkaline solution. So this reaction, it's a weak alkali, isn't it? It's a weak base, a weak alkali. And we can categorize these species according to the Bronsted-Lowry system. So we're looking for the acid on the left-hand side. What is the thing that's donating a proton on the left-hand side? And you can see that it's the water molecule. The water is donating a proton to the ammonia to produce the ammonium ion. Okay, so we designate that acid 1. Its relationship with OH minus is via a proton, isn't it? So that's my base 1. On the right hand side then, this it now has a proton that it can donate. That becomes my acid 2, and that's my base 2. You get it. Okay. A few little notes. Acids that donate 1 proton, typically called monoprotic, 2 protons, diprotic, and then triprotic, etc. Sometimes they're called monobasic, dibasic, tribasic. Lewis' theory of acids and bases, which isn't on the syllabus, is kind of, I'm not going to say obsolete. We don't use it as much. But the idea in Lewis' theory is that an acid is an electron pair acceptor and a base is an electron pair donor. So there doesn't even have to be a proton involved technically. But don't worry too much about that. I mention that just so we're complete. Okay, let's have a look at the acid-base character in different solvents. So we've seen this reaction. We're familiar with that now. Okay. If we mix ethanoic acid with concentrated hydrochloric acid, then we can actually get the ethanoic acid, if you look at this, to accept a proton. It accepts a proton. So the HCl here has given a proton to the ethanoic acid. So that makes the HCl acid 1. Obviously it's related to Cl minus or base 1. Now on the right hand side, the species that can donate a proton is this ethanoate, this strange, it's not an ethanoate ion, is it? It's a strange protonated ethanoic acid molecule. That's my acid 2, and that's my base 2. Okay. We can also get an interesting equilibrium when we mix concentrated sulfuric acid with concentrated nitric acid. So we can get the nitric acid here to accept a proton. So if you look at this carefully, the sulfuric acid is the big bully acid. It's giving one of its protons, so it becomes HSO4 minus, the hydrogen sulfate ion. It forces that proton onto the nitric acid to produce this ion. So that's my acid 2, that's the acid on the right hand side, and that's my base 2. Here we could say that the nitric acid is amphoteric because sometimes it acts as a base, even though most of the time it acts as an acid. We could also call it amphiprotic. It means that it's a substance that can accept or donate protons. Okay, there are questions from the textbook, a couple of pages for you to read just to let these initial ideas and definitions sink in, and then we'll move on.